Okay, so as far as I know, kidney stone is passed. So I'm going to try to give this lecture just normally. Amazon has been selling the second edition for a week or so, and so this is be the last time I'll be passing out paper copies. One student suggested that I post the homework solutions, and I don't have anything against that. It's just that I don't want a PDF of the homework solutions to get distributed to other students who haven't done the homework and so on and so forth. So one of you may have a good idea as to how to do that. Tom may have a good idea as to how to do that.
What's that?
Well, I want to be able to give the students who have done the homework the copies of the solutions, but I don't want a PDF of the solutions to be distributed to arbitrary numbers of students
You can
here
set
and throughout the
a
internet.
password protected area that people can reach.
But
of course, they can still copy stuff.
they can still download it,
Yeah.
right? And
Right.
distribute.
Yeah, it's kind of hard to.
All right, let's think about it. One thing that has occurred to me was I might just print the thing out and put it on the door to my office, and you could just come by and look at the solutions. Presumably you know how to do all the problems, or all but one or two of the problems, and so you're just curious about one step in one of the problems, in which case looking at it on the board would be, on the door of the office would be probably pretty easy to do, I would think. Okay, so the topic now is Fourier series, but I thought before I do Fourier series, let me just give another example. Oh, wait a second. I forgot my coffee. I brought everything here too quickly. Is that a question?
Yes. The homework isn't posted on the website.
Say it again.
The homework isn't posted on the website. I was wondering when it will be posted.
You mean the solutions?
No, the actual homework number 3 isn't on your website.
Well, the homework that's due next week was posted several days ago.
It's not on
the website. The only
The
ones
homework
listed
that's
are
due
one.
next week isn't described?
No.
Okay, well, I'll post it this afternoon after class. Why don't one of you come with me and make sure I do it? Because I'm just really puzzled that it's not there.
So still do Friday.
This is homework that on, well, I don't know. I thought I had put it on the, but when I did that, it was last week, and I had not only the hand surgery, but the kidney stone, and I was on sort of maximum ibuprofen and so forth. So you say I have not assigned the latest homework.
I didn't check. I didn't see it today when I went online.
I just checked. The only ones up there are 1 and 2.
All right. Well, I'll do it later this afternoon.
Will it still be due on Friday?
What?
Will it still be
Yes,
due on Friday?
Yeah, there's some. It's
It
not.
would be the homework due next Friday.
Not this Friday.
This current Friday.
The homework due this current Friday is not online, so.
Number
The
3.
homework due this Friday is still not posted?
It's not
No.
posted.
It was before, it's not anymore.
now it's not there. Yeah. It's gone. Yeah.
All right, I will do something about that. You're saying it was posted and then disappeared?
Yes.
Oh. All right, I can imagine how that might have happened. All right, I'll fix that. I think that might mean that I may have to postpone the homework. Oh, wait, let's do this Friday, so today's only Tuesday. So, all right, well, anyone interested particularly about this, meet with me after class and we'll discuss it. I thought I would do an example involving the curl. Just for good measure. So suppose we have a vector and it just has one component and in spherical coordinates it's a unit vector in the phi direction times the coordinate r. Here we're talking r theta phi. Then what is the curl of V? Well, the curl of V, one of the formulas in chapter 2, in fact not far from this formula here, God, I thought I could. What is going on? This thing is not. This is not responding at all. Well, I guess I'm not going to give a computer lecture. Anyway, the general formula is 1 over r squared sine squared theta times a determinant, which is r hat, r theta hat, r sine theta, phi hat, partial in the r direction, partial in the theta direction, partial in the phi direction, and in this particular case, it's the r component, something times the theta component probably, but the final, those are both 0, and so what we have here is r sine theta, it's r sine squared theta for this particular case where the phi component is r. And so I'm thinking though of evaluating this curl at theta equal to pi over 2, so we're on the equator. And so sine theta is 1, so this goes to 1 over r squared. And again, r hat, r theta hat, r phi hat now, dr d theta d phi, 0, 0, r squared. And so now what survives is the theta hat version. And so this is 1 over r squared from out in front, a minus 1 because it's this column, an r, theta hat, and then an r derivative of r squared, which is 2r. And so altogether, we've got 2 r's which cancel, and we've got a minus 2. So we have minus 2 theta hat. You might find that a little bit weird until you realize that the theta hat vector points, of course, in the increasing theta direction. And the increasing theta direction when theta is pi over 2 is straight down. The theta direction is, theta hat direction is minus z. So minus theta hat is the z direction. So this is effectively 2z hat. And so if we integrate, if we look at the Stokes' formula, it would be that the curl of V integrated over the area, which is then 2z hat integrated over the area, is just twice the area, because z hat is parallel to the area vector. The area vector is perpendicular in the z direction. And so this is twice the area. The area is pi r squared. On the other hand, this is also supposed to be the integral of v dot dl around the whole circumference of theta equal to pi over 2. So we're integrating around the circle, and it is then r the integral, and we have here d phi, r d phi, and as we integrate d phi from 0 to 2 pi, we just get 2 pi, so this is 2 pi r squared, which is of course the same as that. So we're just verifying Stokes' theorem. But I thought that I'd show you that in detail because it exhibits some of the awkward and unusual features of curls in spherical coordinates. My memory is that Fourier was actually analyzing the how heat diffuses in various substances, metals and other substances, water, gas, and it was in that context that it was in order to solve and analyze such problems that he developed Fourier analysis. And I think at the time his ideas met a lot of resistance, but of course we like him very much now. So let's start out with the orthonormality relations of these phase factors. E to the minus I mx over square root of 2 pi, e to the I nx over square root of 2 pi, integrated dx from 0 to 2 pi. Well, this is an integral e to the I n minus m x dx over 2 pi, 0 to 2 pi. And now you just think about it. N and m, of course, are integers. If n equals m, then this is just the integral of 1 from 0 to 2 pi. That's 2 pi. You get unity. So this is equal to 1 if n is equal to m. On the other hand, if n is not equal to m, you can do the integral and evaluate it, and you'll see that you get actually 0. So it's this is the Kronecker delta. These phase factors are orthonormal. And so if we can write a function as a sum from minus infinity to plus infinity of some complex coefficients times these orthonormal phase factors, then that's what's called a Fourier series. And what's remarkable about the Fourier series is that it's so flexible, robust, and capable. That's why it's used so much. And we'll see examples of that later. So now let's suppose we just take the function and integrate it. I'm sorry, not to infinity, 2 pi. E to the I nx, we multiply by the complex conjugate of one of these phase factors. Integrate the function, and what do we get? Well, if we write the function in this way and integrate term by term, then we have an integral fn e to the I. Well, let me make this an m. This is e to the I nx over square root of 2 pi. And then we're integrating here e to the I minus I mx over square root of 2 pi. And we're going to integrate that dx. Then you see this orthonormality relation gives us a sum fn delta nm, and that gives us fm. So the m Fourier coefficient is given by the integral from 0 to 2 pi of the original function times the complex conjugate of the mth phase factor, orthonormal phase factor. Now, Dirac's notation is ideal for describing this arithmetic. And the way we use it is to think about, we're going to represent the phase factors which are orthonormal functions. Each function we're going to think of as a vector n. And similarly, the bras x we're thinking of as vectors also. And I'm going to write this thing as e to the I n x over square root of 2 pi. And so then what we have is that the inner product of m with n, we can write it as m identity operator n. And the identity operator then, well, this orthonormality relation here is just here m x n dx, and so this is equal to the integral 0 to 2 pi e to the I n minus m x over 2 pi dx, and that's delta n m. So that's what this inner product is, substituting a formula that the identity operator is integral 0 to 2 pi, the outer product of these x states, we have that. And on the other hand, these m states are orthonormal, and we can also write the identity operator as a sum of outer products of the n states from minus infinity to plus infinity. So these are two ways of writing the identity operator, the same identity operator. And so consequently, you can think of f of x as an inner product of a vector f, a vector which we represent as a ket f, an inner product of that with another ket x, and we can insert the identity operator, and if we do that, what we get is the sum n equals minus infinity to plus infinity xn n f and this is the sum e to the I n x over root 2 pi n f, and we can think of it, we can write these e to the I n x over square root of 2 pi f sub n. So this is the nth Fourier coefficient. And we can also, the inverse relation is that the nth Fourier coefficient is the inner product of the ket n with the ket f. And if we stick in an identity operator, then, and in particular stick it in the form of an integral 0 to 2 pi outer products of x's with an f dx. This is then an integral e to the minus I n x over square root of 2 pi f of x dx. We can also write the inner product of two states, or two state vectors, or two kets, by inserting the identity operator this way. And this is then the complex conjugate of the nth Fourier coefficient and of G and the nth Fourier coefficient of F. And if instead we stick the other identity operator, other form of the identity operator in, we have G x x f dx like that, and that is an integral G star of x f of x dx from 0 to pi. And these relations, which are obvious in Dirac notation, tell us that if the two kets are the same, then ff is equal to a sum of nf absolute value squared, or a sum absolute value of f sub n squared, which is also the same as integral 0 to 2 pi, the absolute value of that inner product squared, integrated dx. And another way of writing that is integral 0 to 2 pi of the absolute value squared dx. So what this shows you is that the length or the norm of a vector is either the sum of the absolute value of its Fourier coefficients, or it's the integral of the absolute value of the function squared over the domain of the function. And this is a very general relation for Fourier transforms. And it's one of the nice features of Fourier transforms. Now, two things that I need to say at this point are, first, that we've been considering complex functions, but we could also consider a real function, and if the function is real, then, sorry, there's not an X there. The function is, if you take the complex conjugate of the function, what we get is, my eye is a little weird, but I didn't mean anything by it. And now we can see that because we've complex conjugated it, this is also a sum of f minus n star e to the I n x over the square root of 2 pi. So we can write fn star this way. So this is true for a general function, whether it's real or complex. But if it is real, if f is real, then this is equal to f of x. And so then what we can say is that this is the same as well, here, let me just go to the next equation here. What we have is that f sub n so this is the Fourier expansion for the complex conjugate function. So we can say that the nth Fourier coefficient of the complex conjugate function is f star sub minus n. So the nth Fourier coefficient of the complex conjugate function is the complex conjugate of the minus nth Fourier coefficient of the function. So if f is actually real, then this is equal to fn of f, because f is real. And so then we have this, the statement that fn of f, which is equal to fn of f complex conjugate, is equal to f star minus n of f. And this says that f minus n complex conjugate is equal to f sub n. So if real, f real. So if f is real, then it's minus n, the complex conjugate of its minus nth coefficient is the same thing as its nth coefficient. So there are various examples in the book. One Fourier series is the Fourier series of an exponential. Another one is the Fourier series of beats. And so far, I've been using an interval 0 to 2 pi. And that's a common choice. But one could do Fourier analysis on any interval of length 2 pi. And so we could define the Fourier coefficients this way, for example. We could say, well, they go from r to r plus 2 pi, e to the minus I n x, f of x, dx over square root of 2 pi. So that's another choice. And if the function f is periodic with period 2 pi, then it doesn't matter which interval you choose. So if f of x plus 2 pi is equal to f of x, then fn is independent of r. So it doesn't matter which interval you choose as long as it's of length 2 pi. On the other hand, the utility of Fourier series is that you can represent pretty much any function. Just an enormous variety of functions you can represent pretty well as a Fourier series. And so then, if they're not periodic, what happens? Well, the Fourier series is automatically periodic, because the Fourier series is f of x is a sum f sub n e to the I n x over square root of 2 pi. So this is automatically periodic. The series is automatically periodic with period 2 pi, because these functions are periodic with period 2 pi. So if we have a function that's not periodic with period 2 pi, and in fact almost no of them, the vast majority of functions are not periodic with any particular period, let alone period 2 pi, but we can still represent them as Fourier series. And so what's true? Well, the Fourier series representation is periodic with period 2 pi, even though the function isn't. And so then what happens is, if we choose a particular interval from r to r plus 2 pi for a non-periodic function, and we represent it by a Fourier series, this will represent the non-periodic function faithfully in this interval. Outside the interval, it will be periodic with period 2 pi, and probably won't look anything like the original function. So it will be true. So the Fourier series for a function is in general faithful to the function only within the interval in which you do the computation of the Fourier coefficients. So you can choose the interval for anything as anything you want, and obviously one normally chooses a very simply defined interval, 0 to pi, minus pi to pi, something like that. The other question is, you notice that I had to put a 1 over square root of 2 pi everywhere. You can, if you want, segregate the 2 pi's and put them all in one place. So one possibility is you say, oh, f of x is going to be this, dn e to the I n x. But in that case, your dn's are 1 over 2 pi integral 0 to 2 pi dx e to the minus I n x f of x. So if you want, you can put the 2 pi's there and not use them in the phase factors. Or you can say f of x is 1 over 2 pi some cn e to the I n x, and then your c's and n's are minus pi to pi, or 0 to pi. Well, for some reason I chose minus pi to pi. F of x e to the minus I n x dx. So there I've chosen a different interval. But in any case, you have to wind up putting the 2 pi's one place or the other. So when you're doing problems or calculations or working as a professional physicist, you've got to remember that in any particular problem, you can choose the interval any way you like, you can put the 2 pi's anywhere you like, but you can't move them around. In other words, you can't go from the symmetrical convention that I started with and switch to this in the middle of the same problem, or switch to that in the middle of the same problem. So you've obviously got to be consistent with your definitions. The easiest one to implement, I think, is the one that I outlined in the beginning of the class, namely the one that's symmetrical, where you have square root of 2 pi's everywhere. And that way, they just occur all the time, and so you don't need to wonder whether the square root of 2 pi goes here or not. Okay, I think I'm going to skip the next example. So we were talking a moment ago about real functions and that they had special, simpler coefficients. So let's expand a real function, and just to avoid the 2 pi's, I'm going to use this convention for now. And so I'm going to write this as I'm going to take the first one as d0, and then I'm going to have a sum n equals 1 to infinity dn e to the I nx plus d minus n e to the minus I nx. So this is the Fourier series. On the other hand, I'm saying that f is a real function, and so d minus n is dn star. So this is dn e to the I nx plus dn star e to the minus I nx. And now we can expand e to the I nx as cosine nx plus I sine nx. E to the minus I nx is cosine nx minus I sine nx. And if we do that, I think I'll skip one step here. What we find is that this is d0 plus a sum from 1 to infinity of dn plus dn star cosine nx plus I dn minus dn star sine nx. So that's what the sum looks like, and we can represent these combinations as an equal to dn plus dn star, bn as I dn minus dn star. So notice that although the function f in this case is real, the Fourier coefficients are not real, but the combinations of Fourier coefficients that enter the expansion of the Fourier series in terms of sines and cosines, those coefficients are real. And so what we have is f of x is a0 over 2 plus a sum n equals 1 to infinity an cosine nx plus bn sine nx. So this is probably the most famous form of the Fourier series. I didn't start with it because it's much easier to derive everything in terms of complex arithmetic than real arithmetic. It's one of those mysterious things that sometimes complex numbers are just better for what you need to do than real numbers. I don't know why that's true. So, there are simpler ways of, these dn's, of course, are like this. If we take these formulas for dn and use these definitions of an and bn, what we find is that an is the integral 0 to 2 pi of cosine nx times f of x dx over pi, not 2 pi, and dn is an integral 0 to 2 pi sine nx f of x dx over pi. So the Fourier coefficients for a real function in terms of sines and cosines, or cosines and sines, are the cosine and sine integrals 0 to 2 pi divided by pi. So these are very nice formulas, and they're what, I guess they were the well, when Fourier series were taught to people who didn't know about complex numbers, I guess this was the form that was used. And there wasn't any mention of e to the I nx. But without e to the I nx, it's hard to know what's really going on. I wrote down some orthonormality relations of sines and cosines. Those are the real analogs of the complex orthonormality relations that I started the class with. Okay, so once again, the Fourier series had the advantage of being able to represent almost any function. What is true, though, is that you represent the function quite well within the interval in which you compute the coefficients. Outside that integral, what you have is a periodic function of period 2 pi that is similar to the function inside the interval. And so one of the problems of Fourier series is that, for example, suppose you want to represent let's suppose you want to represent the function f of x equal to x on the interval minus pi to pi. Well, obviously, the function x is not a periodic function. It's a monotonic function. And if you compute the Fourier series and graph it, well, I did that in an example in figure 3.4, and between minus pi and pi, if that's x, the representation is pretty good, but it gets kind of jittery here. And the reason it gets jittery here is that the Fourier series is periodic, a period 2 pi. And this is minus pi, and this is pi. So this function, this Fourier series knows that it's got to be equal to minus pi at pi. And yet it also, if it's going to be represent x, it has to equal pi at pi. Those two numbers differ by 2 pi. And so it goes nuts here. And what happens is it effectively starts down here again and goes up. So the actual Fourier series looks like this, with jitters here, and here, and here, and here, and here. And these are things that were studied originally by Gibbs. I don't know if he was the first, but he was the first famous person to study the Gibbs overshoot. And by the way, it sometimes turns out that physicists turn out sometimes to be heroes in social life, not simply in intellectual life. One example is the Gibbs family. Gibbs's father was a linguist who served as a translator for the Africans who revolted on the slave ship Amistad that was made into a movie some years ago. And he helped the New England lawyers get the Africans freed. I don't remember if they went to the US or went back to Africa, but they didn't get killed, as I remember. Another example was Max Planck. In this case, it was his son who tried to assassinate Hitler. Unfortunately, the bomb was in the wrong place, and Hitler survived, and Max Planck's son was killed, was executed by Hitler. Another example that's more verbal than anything else is you can look at Einstein's positions on human rights, and you'll see that he was a very decent man and espoused the sort of values we could all greatly respect. So far I've been talking about intervals of length 2 pi, and I've said, well, you can move them around a little bit. You can also stretch them. And in fact, most often in physics, we don't restrict ourselves to intervals of length 2 pi. We use an interval of length L and use whatever L we want. And in fact, what we often do in physics is we say, well, L is just an arbitrary number. It might be infinite, in which case we have Fourier integrals. And that'll be, of course, the next chapter. So let's look at the case where we do an integral of length L. So then the phase factors are e to the I 2 pi nx over L over square root of L, complex conjugate. So I've got this figure here that's making things a little bit. Okay, that times e to the I 2 pi mx over L over the square root of L, and this is delta NL. So that integral of length L shows that these phase factors are orthonormal on the interval of length L. And the corresponding Fourier series is f of x is a sum n equals minus infinity plus infinity f sub n e to the I 2 pi nx over L divided by square root of L. So this is the general form of the Fourier series. Again, though, I've chosen to go from 0 to L. You could go from minus L over 2 to L over 2. So we'll R to L plus R. This orthonormality relation together with this relation tells you that f sub n is equal to an integral 0 to L e to the minus I n x, well, I left out the 2 pi, over L over square root of L f of x dx. So these are the formulas for the Fourier coefficients, and the analog of that sum over there is that the sum of the absolute value squared of these Fourier coefficients is equal to the integral from 0 to L of the function, the absolute value squared of the function over the interval of length L. And so what you see in the case of Fourier series, once again, is that you expect the function to be square integrable on the interval, at least if the Fourier coefficients, the absolute value of the Fourier coefficients sum up to a finite number. So once again, if you want, you can shift the integral, and you can also I don't know what I was going to say there. In the case of a real series, the series is f of, the function is real, then you can write it this way, and a0 over 2 plus the sum from 1 to infinity and cosine y and x over L plus bn sine 2 pi and x over L, and your an are intervals 2 over L, 0 to L, dx cosine 2 pi and x over L, f of x, and bn is 2 over L, 0 to L dx, sine 2 pi and x over L. Okay, so these are the Fourier relations for a real function expanded on an interval of from 0 to L, arbitrary length L. Now, if you have a function of 2 variables or 3 variables, you can also use Fourier series, as you might imagine. And so what you do is you simply use, do this. Maybe I'll go over here. Running out of space faster than time. So suppose this is fx1 xn, then this would be a sum n1 equals minus infinity plus infinity. Let's make this an m. N sub m equals minus infinity plus infinity. F sub n1 nm e to the I 2 pi n1 x1 plus n2 x2 plus nm xm over L, and divided by L to the m over 2. And similarly, f sub n1 nm would be integral 0 to L dx1, 0 to L dxm, e to the minus I 2 pi over L, x1 n1 plus x2 n2 plus xm n sub m. I should have used k instead of and divided by L to the m over 2. So these are the multivariable Fourier relations. You might at first glance think, oh, these are absurdly complicated, why would anyone bother? Well, it turns out that if you're doing electrodynamics or quantum electrodynamics or quantum field theory or anything in three-dimensional or three-dimensional space or four-dimensional space-time, the natural thing often, or the convenient thing, is to expand things in Fourier series or Fourier integrals, and then you have these in products here. And in those cases, what plays the role of these integers is typically, you see, you have n over L. So if L is a length, this is something actually with dimension. And these things are typically momenta, or momenta. Or what one has is x dot k, or often it's just written as xk, and what is meant in four-dimensional space-time is x dot k vector minus x0 k0. So minus the time component and the energy component. This is the space component and the ordinary momentum component. So four-dimensional Fourier series and integrals are extremely useful in physics. Now, the next topic is just integration or differentiation of a series. And let me, I guess, show you the simplest example is, let's suppose we have a nice continuous function here. Actually, I don't know if that's is continuous. I drew it as if it were continuous, but it's not actually continuous. So this is a discontinuous function. So let's instead go up one so that we have something that's continuous. So let's suppose we just look at this. This is something that is certainly continuous. Here the derivative is constant, and then it changes in value. So the derivative of this function is changing in a way that's discontinuous, like this. On the other hand, this thing is discontinuous, and if we take its derivative, we get a Dirac delta function. In fact, this thing is sort of the mirror image of this. If you have this be negative, this be 0, this be 1. So you have a function that's 0 on the negative real axis, 1 on the positive real axis. This function is called the Heaviside function, theta of x. And the amusing thing about it is the function has one side that's heavier than the other, because one side has unit weight, the other side has 0 weight. But the man who invented its name was actually Heaviside. Anyway, if you look at this function is not continuous, but at least it's only just sort of mildly discontinuous. But the derivative of the Heaviside function is a delta function. So theta prime of x is actually delta function of x. So in general, when you differentiate a function, you get something that's rougher and rougher, more and more singular. On the other hand, if you integrate a function, what you do is you get a function that's smoother and smoother. And this is particularly clear in terms of Fourier series. Suppose we have the series f of x equals some fn e to the I 2 pi n x over L, or the square root of L. If we integrate, what we get is a function whose Fourier series is f of x, which if I leave out a couple of terms, there are terms like this, f sub n over n. The actual formula is equation 3.58. But the point is, if you integrate this with respect to x, you bring down a factor of n for each coefficient. And so when you integrate, you get a Fourier series. This series converges better than that series because there's an extra 1 over n in the denominator. So the high frequency terms are damped out. On the other hand, if you differentiate this function, you bring down a factor of n, the high frequency terms are amplified. And so basically, you have a rougher, more singular function. And the convergence isn't as good. So now, in general, let me just say a few words. I've got maybe 12 minutes or so to say something about continuity and convergence and so forth. And I would say the best thing is for you all to study the text, because I don't think I can if you don't know this stuff already because you learned it in undergraduate school, then I don't think I can teach it to you in 10 minutes. It's something that's normally taught in a course over a period of weeks. So let me just think about it this way. Let's imagine we then have a sum. The Fourier series is a limit of this sort of a series. It's the nth Fourier coefficient, e to the I, 2 pi, and x over L over the square root of L. And of course the Fn has its standard formula. And so we're now asking, how well does a Fourier series converge to the function? How well does this converge to the function f of x? Well, what's clear is that whatever it does, it converges to the periodic extension fp of x in general, because most functions are not periodic of period, let us say, L. So this converges to the periodic extension of the function of period L. And so the periodic extension is just that you take the function as defined on the interval, and then in each successive interval, you write the function, you just repeat, you force the function to be periodic. And now, what do we mean by convergence? By convergence, what we mean is f of x minus f sub n of x. That this can be made as small as possible as long as we go far enough out in the sequence, that is to say, n is bigger than some n that may depend upon how small we want epsilon to be and which x we're talking about. So it would depend upon epsilon and x. So so we say a Fourier series converges on a certain interval if for every epsilon greater than 0 there exists a capital N depending on epsilon and x, such that f of x minus f sub n of x is less than epsilon as long as we're further out in the sequence than capital N. This is the general case of convergence. We don't always have convergence, but very often we do. And if the n is independent of x, then we say the convergence is uniform. let me remind you of what is meant by a function that's continuous. First of all, f of x minus 0 is a cute notation that means limit of f of x minus epsilon, where epsilon goes to 0 and epsilon's always positive. So that's a limit, or a definition of a limit. F plus 0 is the same thing, except that now it's f of x plus epsilon. And again, 0 less than epsilon going to 0. If f of x plus 0 equals f of x minus 0, if the two limits are equal, then the function's continuous at x. If it's continuous at all x, well, then it's continuous at all x. So continuity, of course, is a nice thing, and roughly it means that you can draw the function on the board with chalk, although you're not supposed to go first. An interval AB is the set of all x greater than A less than B. The closed interval AB is the set of all x greater than or equal to A less than or equal to B. And there's a nice property that functions have that are continuous on a closed interval. A function that's continuous on a closed interval is bounded on the interval and integrable on the interval. So we're basically home free if the function is continuous on a closed interval. If the interval is open, then funny things can happen at the boundary. And an example of a function that's not integrable, 1 over x on the interval 0 to 1, it's continuous on 0 to 1, but it's not continuous on and bounded on the closed interval 0 to 1 because it's infinite at 0. Now, in a course of on analysis, one proves various things, such as that a sequence of continuous functions converges uniformly to if a sequence of continuous functions converges uniformly to a function on a closed interval, then we can draw a certain conclusion. And the conclusion we can draw is that the function can be integrated term by term. And the reason is that we have the function, the series up to Fn so the difference of the two integrals is less than or equal to the integral AB of the absolute value of the difference of the two functions. And if the convergence is uniform on this closed interval, then we can make this arbitrarily small, in which case this goes to 0. And so we can say that the Fourier series converges to the integral, and also the integral of the Fourier series converges to the integral of the function. So you can integrate Fourier series term by term if the Fourier series is uniformly convergent on the interval over which you're integrating. So I mentioned that that I shouldn't have called this function continuous, even though I could draw it with chalk. But we can call this function piecewise continuous. And a piecewise continuous function is a function that's continuous except at certain points where it's discontinuous, where it has finite jumps. So essentially, if you can write it on the blackboard with your fingers, it's piecewise continuous, because you're able to go vertically on the blackboard. Now, if you have a function that is piecewise continuous, but not continuous, so that it does have finite jumps, you might ask, what is the periodic extension of the function? Remember, the periodic extension I said was you just extend it periodically outside the interval. Well, there's another thing you do for a function that's piecewise continuous. You define the value of the function at the jump to be the average of the value of the function before the jump and the value of the function after the jump. So you take the average. So the piecewise continuous function goes along here, jumps to here, and then it goes along here. That's the piecewise continuous function. And so with this definition, I can state the convergence theorem, the fundamental convergence theorem for Fourier series. And it is that the Fourier series of a function that is piecewise continuous with a piecewise continuous first derivative converges to its periodic extension. So let me say this again. You have a function that's piecewise continuous and it has a piecewise continuous first derivative. Then its Fourier series converges to the periodic extension of the function. So we basically have the Fourier series always work rather nicely for functions that are piecewise continuous with piecewise continuous first derivatives. So if a function has a piecewise continuous first derivative, then its Fourier series converges to its periodic extension. So that's very nice, but it's still somewhat more restrictive than the use we actually make of Fourier series, because Fourier series can do a reasonable job of representing functions that don't have piecewise continuous first derivatives. But still, when you think about it, I mean, by saying piecewise continuous, you're allowing an arbitrary number of discontinuities in the derivative at least. The convergence, by the way, in this case, is uniform on every closed interval on which the function is continuous. Okay. Another definition, I'll just leave you end the class with this definition, is something called CK. Functions that are CK. CK means that kth derivative is continuous. And in fact, many of the functions that I looked at as examples of Fourier series were in actually C0. They had no continuous derivatives at all. All right, so let's can you please turn off the video, unless there's a final question? Okay, let's,